Welcome, viewers, to Bodhi Unified Flow. Here we simplify complexity and amplify performance. Today, we're embarking on a really fascinating journey, diving right into the very heartbeat of operations management. We're looking at the groundbreaking text, Factory Physics by Wallace, Hopp, and Mark Spearman. Specifically, we're going to dig deep into part one of their work. This covers the critical introduction to factory physics and, honestly, some incredibly vital, yet often completely overlooked lessons that we have got to learn from the history of manufacturing. Okay, let's just quickly glance at our roadmap for today's explainer. We'll start with 1, the blizzard of buzzwords, then move to 2, the lessons of history. After that, we'll look at 3, a science of manufacturing, followed by 4, the laws of variability, and we'll wrap it all up with 5, summary and references. By the end of this session, you're going to firmly grasp the underlying, highly predictable behaviors of your manufacturing systems. We're going to trace exactly how modern operations evolved to where they are today. You'll understand the profound limitations of simply, chasing the latest industry trends. And most importantly, and this is a real game changer, you're going to learn exactly how to buffer variability to absolutely amplify performance in your own operations. All right, let's get into section 1, the blizzard of buzzwords. So, you know how it is. For decades now, the field of manufacturing has basically been besieged by one so-called revolution after another. We've seen material requirements planning, just-in-time, lean, Six Sigma, agile. The list literally goes on and on. Now, don't get me wrong. While each of these undoubtedly contains really useful, highly effective insights, they're almost always presented with this fire-breathing, revolutionary rhetoric. They're treated like isolated tools, or worse, short-term management fashions. Think about it. A company adopts lean this year, Six Sigma the next, and everyone on the floor just ends up suffering from massive initiative fatigue. Instead of endlessly chasing these isolated trends without any real foundational context, we desperately need a unifying scientific approach. We need a solid framework that actually provides the overarching understanding you need to choose between these techniques or to combine them effectively. We should be making decisions based on actual physical principles rather than just the latest catchy slogans. Moving right along to section 2, the lessons of history. To really understand why this unifying science is so urgently needed today, we kind of have to trace our steps backward. Manufacturing has been on quite the journey. It evolved all the way from the highly skilled artisan's bench, where every single thing was custom-made, slow, and naturally very variable, right through the first industrial revolution. By the mid-1800s, the American system introduced interchangeable parts, and that completely revolutionized consistency. Then we scaled things up massively during the Second Industrial Revolution. You had leaders like Andrew Carnegie who absolutely mastered the economies of massive scale, specifically in the steel industry. But as we found out, sheer scale just wasn't enough. Henry Ford came along and realized we needed extreme speed and continuous flow. He literally changed the world with his moving assembly lines. And shortly after that, the entire process of human labor was strictly formalized by a guy named Frederick W. Taylor. Now, I want you to notice the profound contrast between these two particular pioneers of the early 20th century. Look on the left here. Henry Ford was totally, single-mindedly obsessed with speed, with flow, and with eliminating any unnecessary material handling. He looked at the whole system as one continuous, flowing river. But then on the right, we have Frederick W. Taylor. He brought a very rigid, microscopic structure to the floor with his famous time studies. Crucially, and this is a big deal, Taylor separated the planning of the work from the actual execution of it. So while Taylor's approach did bring a much-needed dose of scientific management to the factory floor, it also introduced this really rigid and sometimes detrimental division. A hard line was drawn between the management sitting in the office and the workers actually sweating on the factory line. Yet despite all these incredible historical breakthroughs, the massive scale, the unprecedented speed, the rigid standardization, modern operations eventually fell short. Why did that happen? Well, Albert Einstein actually hit the nail on the head here. He brilliantly noted perfection of means and confusion of goals seem to characterize our age. And that's exactly what happened to us. We perfected our means. We built these incredibly complex MRP software systems. We deployed highly precise robotic assembly lines. We optimized the efficiency of individual machines down to the millisecond. But we became completely confused about our overarching goals. We got so heavily focused on keeping our machines utilized to 100% capacity that we entirely lost sight of the actual profitable flow of value to the customer. Which brings us nicely to section 3, a science of manufacturing. This historical confusion we just talked about, this heavy reliance on perfectly executed tools without an integrated strategy, it forces a necessary shift. We absolutely must move away from treating manufacturing as a craft or as some buzzword-driven fashion and start treating it as a hard science. So, how do we define factory physics? It is a systematic description of the underlying behavior of manufacturing systems. Look, it's not factory magic. It is a systematic, reductionist science that focuses entirely on the basic, entirely predictable behaviors of production lines. Think of it like this. Just as a civil engineer utilizes the fundamental laws of physics to build a bridge, knowing for a fact that it absolutely will not collapse under weight, a manufacturing leader has to utilize factory physics to build a production system that will not fail under stress. It's the exact same logic. Developed rigorously by Wallace, Hopp, and Spearman, this powerful framework strips away all that confusing jargon. It provides the solid, scientific intuition that near buzzwords completely lack. It relies on the scientific method to provide a descriptive model of how a plant actually behaves in the real world. It meticulously connects your critical measures, things like throughput, inventory, capacity, and cycle time, through very concrete mathematical and logical relationships. Ultimately, this gives managers the actual tools they need to make predictable, guaranteed improvements. Okay, let's dive into Section 4, the laws of variability. While the underlying math here is absolutely critical, such as Little's law, which elegantly proves that your work in process simply equals your throughput multiplied by your cycle time, it's the fundamental intuition behind the math that truly matters. If you just shove more and more work into a system without actually increasing the rate of throughput, the time it takes to complete a product simply must increase. It is inescapable physics. There is no way around it. These mathematical laws prove a rather harsh reality for us. Whenever there is a lack of perfect synchronization between what your customer demands and what your factory's transformation process can output, chaos ensues. It's randomness, not just a lack of effort, that is dictating your physical outcomes. And this brings us to what is arguably the most unforgiving critical law in all of operations, the law of variability. It states very plainly that increasing variability will always degrade the performance of a production system. Think of it exactly like traffic on a highway. When every single car is driving at the exact same speed, with the exact same distance between them, the flow is absolutely perfect. The highway handles massive throughput, right? But introduce just one erratic driver, one sudden lane change, that's variability. And what happens? The entire system slows down to compensate, creating one of those frustrating phantom traffic jams. Well, your factory is that highway. Whether it's variability in process times because a machine broke down, or variability in quality that causes rework, or even unexpected spikes in customer demand, any randomness will force your system to compensate, and your performance will absolutely plummet. Because of this inevitable degradation, variability must be buffered. The laws of physics dictate that a system can only absorb this chaos through three very specific mechanisms: inventory, capacity, or time. I want you to consider your own operations for a second. If your process is highly variable and you absolutely refuse to make your customers wait, meaning, you cannot use time as a buffer, you must pay for that variability somewhere else. You have to. You must either hold massive, expensive inventory to cover those unpredictable spikes, or you have to buy excess capacity. And by that, I mean buying expensive machines or hiring labor that literally just sits idle half the day, just so they're available to catch up when things inevitably go wrong. You cannot escape this physical law. You can only choose which buffer you are willing to pay for. Now, when we look through this scientific lens, a lot of these popular methodologies finally start to make foundational sense. Take a buzzword like lean manufacturing. Suddenly, it takes on a much more precise, actionable definition. Instead of just meaning this vague elimination of waste, lean simply means achieving your fundamental business objectives with the absolute minimum buffering cost. That's it. It means systematically stripping out variability from your processes so that you no longer have to pay for that excess inventory or that idle capacity or those frustrated, delayed customers. Science replaces the buzzword. And finally, Section 5, Summary and References. Let's pull all of these vital concepts together. We've seen how the long, fascinating evolution of manufacturing led straight to our modern complexity. But by actively transitioning away from isolated buzzwords and utilizing the real science of factory physics, you can actually scientifically manage your operations. By understanding that variability is the ultimate enemy here, and by proactively managing those three universal buffers, inventory, capacity, and time, you can take total, predictable control over your plant's performance. So I want to leave you with this final provocative thought to really examine within your own organization. Are you making your operational decisions based on fundamental, predictable physics, or are you simply paying for chaos while blindly following the latest manufacturing fashion? because true operational excellence absolutely requires understanding the unbreakable science behind the system. Thank you so much for joining this explainer today. Here are the key references we cited, specifically that essential text by Hopp and Spearman, to help you further your own journey into scientific operations management. Keep learning, keep simplifying that complexity, and we will see you next time, right here on Bodhi Unified Flow.